Hey everyone, my name is Brett Rudenstein. I'm the Director of Product Management at WANDisco. And today I'm going to talk about selective data replication with geographically distributed Hadoop. So what does that actually mean? I mean, really anyone can take data from one cluster and put it in another cluster. But what becomes really critical and what we've seen over the last couple of years is what the consistency of that data is across multiple geographic territories. In addition to consistency, how relevant the data is, how timely is the data invalidated, just as it makes it to another cluster. And then probably most importantly, and one of the things that we hear continuously, is how do we run our clusters in an active fashion, specifically while sharing the same data set. What if we need to share the same data? Can I have clients writing in? Can we treat a cluster that is distributed across any number of geographically distant locations, whether they're in metropolitan scope to a wide area network across the ocean? Can we treat them as a single cluster and have them act the same way at WAN scope that they do at LAN scope? So there's these sort of dimensions of scalability. And we see over time, we see statistics like, data is growing at a rate of, 60% year over year, sometimes even in the realm of 2x. So there's a lot more data. The data, is created faster, it's ingested faster. There are more objects that we have to look at. Those objects are different sizes. We've got very large file sizes, very small file sizes. And then we've got more clients trying to access the data and use the data. And of course, the problem with that is the more clients that we have running jobs, the busier the cluster gets. And then there's, of course, contention for the resources of the cluster themselves. That's, of course, why people create multiple clusters. We see in a single organization, oftentimes 3 or 4 different silos, but there's the common data set that winds up being shared. Of course, even within a single cluster, at least from the perspective of HDFS, RAM becomes a limiting factor because of the name node having only a finite amount of space. So you will ultimately hit an upper bounds from the name node's perspective. And then there are some other or additional dimensions of scalability, such as the number of locations that you try to traverse across. And again, as I mentioned earlier, either at LAN scope, multiple zones within a single data center, or across metropolitan areas across the country, across the world. So we can look then at scalability as a universal measure for designing a distributed system. So how then can we run Hadoop in multiple clusters across the world and actually have a single user experience? And there are sort of 4 main steps. There's the coordination engine, which is responsible for handling all of the requests by clients. So if we think about it, even in the current implementation, if you look at Hadoop with the standby name node, it has a coordination engine. The name node is the coordination engine for all activities that happen. So what we do is we create a coordination engine at geographic scope, or a distributed coordination engine. Of course, what that coordination engine has to do is it has to understand what is the system ultimately trying to replicate across any number of data centers. And in this case, what we do in an active fashion is we replicate the underlying, the metadata itself. So we fundamentally can break apart the metadata, the actual request for creates, updates, deletes, and so forth, all of the things that change namespace information, and separate that from the underlying data structures themselves, whether that's on HDFS or backed by an Isilon file system or anything of that nature. Probably most importantly is that in stage 2, when you replicate this virtual namespace, you do it in an active fashion, and that is that the behavior of the application isn't changed regardless of where the users are. So in a LAN setup, we would expect that if we both try to create a file at the same time, we were both in the same cluster, I do a create on file foo, someone else does a create on file foo, that one of us gets file created and the other gets file exists. What we often see is that systems that become distributed have to do so in an eventually consistent manner, where both of us are allowed to create the file, and then sometime later the system will come back and reconcile and say, you know what, I know I told you you could create the file, but realistically speaking, you can't create the file. This is how the file was created first, and that reconciliation happens and you have to work around the system some other way. So active means that same behavior is achieved. So even at 3,000 miles distance, if we both entered this file at the same time, we would get the same behavior at LAN scope. Then, of course, just geographically distributing that across multiple data centers and then supporting a variety of use cases. So the one that we sort of naturally think about when we talk about replicating data to a bunch of different locations is disaster recovery. Simply having data from one place and making it available in another in case something goes wrong. But there's a whole lot more that you can do once a file system becomes active-active, and that is you can fully utilize all the underlying resources across all the data centers. So now your backup data center isn't just for backup, isn't just for test or dev, but you can actually use it for production level runs because the data is current, it's fully consistent or strongly consistent, and therefore it is useful at all locations that participate. And then finally, of course, you don't want to replicate everything, you only want to replicate that data that's important. So we create selective data replication for the particular zones. You may have it where some data centers, folder A is replicated to data centers, A and B. Folder, C is replicated to data centers 1, 3, and 5, and so forth. So you determine what the rules are, and this becomes important for issues of foreign sovereignty, data can't leave a country of origin, and so forth. So the requirements of then building a system like this. As I mentioned just a moment ago, it has to be operate or be perceived by the general users as a single system. So it's that unified view regardless of what the underlying users are doing. It operates with strict consistency. Everybody sees the exact same versions of the data all of the time, and that nobody can come in and basically make a change that contradicts another user's change. It's not to say that I can't create a file and someone else can't come in and delete it after the fact. That's a legitimate use case at land scope. So again, that the underlying behavior in application is unchanged. And that, of course, all of the components in the replication engine themselves are continuously available. That they can withstand any kind of fault. That is being able to withstand a fault from whether it be a CPU, whether it be the node that faults, even the network. And probably more likely what we see is lots of random, intermittent hiccups in the network, what we call like to call flapping networks, which traditionally cause problems for most distributed coordination engines because they're not designed with fault in mind. And then, of course, to be able to support more than 2 data centers. I look at sort of the canonical use case when people try to do active-active with sort of out-of-the-box tooling and methodologies. They replicate in a single direction only. It's sort of unidirectional replication. And that's because as soon as you try and do multiple directions, you have to start dealing with things like multiple masterships, where folder A replicates from DC1 to 2, and folder B replicates from DC2 to 1. And then if you start throwing in a third and a fourth data center, that web of complexity gets significantly complicated by all of the relationships that you have to manage and the directions of that data that you have to manage. So we have 2 basic architectural principles to basically provide this strict consistency and allow not only continuous replication and active-active replication of the data, but at the same time give you land speed performance. Because one of the classic things that we see in a lot of systems that try to go distributed is the application then is slowed down while we wait for data to replicate across the wide area network. So the 2 fundamental principles are, first, we use the coordination engine to replicate the metadata between the systems. In this particular case, what we're replicating, since we talked about a virtual namespace, is we're replicating the individual file opens and the file closes. Each time a file is added to the system, we are managing that. So if I open a file in data center 1, then it opens in data center 2 and potentially 3 and 4 if it's replicating to all those locations. Then we transfer the data and then close the file, all at the same time while allowing multiple users in other data centers to do the exact same thing. So active-active also means that there's no time slots for individuals, that everyone can ingest, everyone can modify the namespace at the exact same time, and the system can handle concurrent agreements and operations. So we provide, again, by using the coordination engine, which I'll go over in a few minutes, we provide that strict consistency of the data. The second part, of course, is the data itself. How do we make sure that we get the data between the data centers? And we do that in an asynchronous fashion. So by blocking a file once a file is created, no one else has the ability to write into that file foo that we create, and then we asynchronously stream the data into the opposing data centers from a number of different locations. So now, how does that coordination engine work? Well, I'll take a tiny step back and look at what a coordination engine, some basic principles of a coordination engine, and then talk about sort of the two types of coordination engines, central and distributed. So a coordination engine ultimately ensures that everything that goes into it is executed in the exact same order by the proposers or the people that submitted the requests into the engine. So that follows a fundamental tenet, security considerations aside, one that anybody can propose. So any number of users can access the system and send a request inside the system and ask the system to do something, create a file, append to a file, delete a file. And the engine then chooses one agreement at a time to actually execute, and it guarantees that the engine will execute them by a learner, if you will, to execute them in the exact same order. So the agreement triggers a corresponding action, which is the actual creation of the file inside the namespace and ultimately inside of HDFS if HDFS is on the back end. So in a centrally coordinated system, this tends to be really easy to do because you only have one box. So an example of a central coordination system is Hadoop's name node. Understanding aside from the fact that Hadoop has some HA capabilities, so if it fails, another node will take over. But you've got to keep in mind that the name node can only handle requests going to one name node at a single point in time. So that is a central coordination engine. Everything goes through it. It therefore is the reason that the name node is the performance bottleneck, the availability bottleneck, and why you have an upper bounds on the amount of RAM that you can throw at it, and therefore the amount of files or objects that you can ultimately put inside the file system. And it's a single point of failure, so then you create HA mechanisms for failover. So again, example of a central coordinated engine. So what about a distributed coordination engine? Well, this operates on a principle of using lots of nodes, a quorum of nodes, if you will, to ensure that the same deterministic state can be achieved by every data center and all nodes that participate. And there are a couple of roles in a coordination engine. There's the proposer role, which is designed to take an agreement or some object that we want to create or some file that we want to create and make a proposal into the system. Then there's a set of acceptors. Those acceptors, of course, are there to form a majority quorum. And if the majority agree that the next monotonically, incrementally, what we call global sequence number is the next item to go in sequence, then the acceptors, once they agree on it, they will pass it on to the learners, and the learners at all locations, because there are now multiple, it's a distributed coordination engine, all of the learners execute that agreement at the exact same time. So that's essentially how a distributed coordination engine works. We use a consensus algorithm to guarantee that same state is learned on every single one. And we use this idea that I mentioned a moment ago called GSN, or a global sequence number. And what's nice about the GSN is it provides logical time. So we get the exact same deterministic state at all locations so that we can provide active-active. So every time an agreement is sent into the system, that system assigns a unique global sequence number, or GSN. It is guaranteed to be a monotonically incremented number of the last global sequence number. So if the engine agreed that the last number was 5, then the next one will guaranteed to be 6, and so forth. And it's important that when the system comes online, that all of the locations that participate start with the exact same state. And that way, every subsequent operation ensures that there's a deterministic state between them so that you can have multiple Hadoop clusters across multiple geographies, all providing active-active replication of the data. We base this information on the well-known Paxos algorithm, but we've made a number of enhancements to Paxos to allow Paxos to be replicated over a wide area network, to be high performant, allow multiple proposers, multiple acceptors to handle any given set of agreements at the exact same moment in time. So I'll talk about coordinating then the replication of the HCFS namespace. So most of us are familiar with HDFS as the underlying file system for Hadoop. If you go up one level in the stack, there you come to HCFS, or what's called the Hadoop compatible file system. HCFS is what all of the other vendors use in order to write, basically to become clients into the Hadoop stack. So Isilon, S3, any of the other any of the other distributions, MapR, they'll all use the HDFS in order to provide access into the underlying system, regardless of whether it's backed by HDFS or another file system itself. So what we're effectively doing then is we're letting this, what we call fusion nodes, coordinate a virtual namespace, where every time a user puts a file into a specific replicated folder, the fusion nodes act as a client proxy. So the clients are able to send their request to the fusion server. This is all sort of somewhat invisible to the end users. They're not really aware that this is happening underneath the covers. But what's happening is the clients make a request to HDFS file system. It's intercepted or it's proxied by the fusion server. That acts as a proxy for the file opens and file closes. Any read in the system is essentially a pass-through. We don't have to coordinate reads. And that ensures that the namespace is consistent with each other. So this offers essentially a very strong and very strict consistency model. So for data, again, that's timely, that data that requires continuous replication as opposed to periodic replication, you can ensure that you have a much more even distribution of your network load. Rather than having, the sort of status quo, the typical model of replicating between data centers, such as DiskCP, kick off every 6 hours. You have a much more even distribution of network across the, of load across the wide area network. The Fusion replicated folders have identical states when they reach the same GSN number. So even though technically at any moment in time, at any moment in clock time, that is, they can have different states or have different agreements going on. In logical time, they will all have the same exact state. And again, that's what allows you to provide active-active utilization of the underlying file system. So the fundamental tenet here is that the system acts, again, and I know this is a little bit repetitive, but the system acts as a single system across any number of locations, so that a user in the UK, for those files that are replicated, ultimately share the exact same experience as a user in, say, the US. The parts of the cluster are on different data centers. They should effectively have equal roles, so that data is able to be accessed across all locations, and that the data ingest itself should happen at land speed. And so the way that we achieve land speed is by separating the metadata from the underlying data stream. So by only coordinating metadata, we can allow a single data center to move on to the next file without having to wait for the full file transfer to occur. It also needs to account for any failure scenarios. So any node that fails in the replication process, such as the inter-Hadoop communication process, the Fusion node itself, a WAN partition shouldn't bring down the system, and probably most important, that your RPO, your recovery point objective, is as low as possible. As fast as the data will be allowed across the network will be the lowest RPO that you can achieve for both the purposes of recovery and, of course, for active utilization of that underlying data. This is just a quick depiction of how the system actually works. In the Fusion workflow, a client makes a request. So following the numbers, our client says, I want to create a file. So the client makes a request into the system. It's intercepted or proxied by the Fusion node. The Fusion node then, on behalf of the client, writes that file, or rather, in step 2, the Fusion node coordinates, using that coordination engine that we talked about, the metadata. So the first thing it does is it coordinates the file open. And so for that file that we've just added, both Data Center 1 and Data Center 2 open the file at the exact same time, or at least as close as possible in time that they can. Once the file is opened, then the Fusion node writes the data. The Fusion nodes are writers, so it writes the data into the cluster where the user is sitting. So step 3 there. Once the data is written into the cluster, an IHC service, which is what we call the inter-Hadoop communication server, or inter-Hadoop compatibility server, will read that data across the wide area network And once the data is fully realized in the second data center or the third or fourth data center, then there's another coordinated operation in step 5, which is the file close. And then it can go on to the next operation. So this basically allows us to ensure that strict consistency model. What's also interesting about the inter-Hadoop communication service is because it operates at the HDFS level, the HDFS API, we can interact with any of the underlying storage systems. So we can go operate on an Isilon back cluster, a MapR back cluster, an HDFS cluster, or something in Amazon S3, or really any other HDFS compatible file system. Additionally, we can support a replication between different vendor distributions. So you can go between, say, a Hortonworks and a Cloudera. You can also go between different versions of those. So you can go between an HDP 2.0 and an HDP 2.2 cluster and still provide that same active-active. So when it comes to actually performing upgrades, maintenance releases, and things of that nature, you can keep the system fully active, completely replicate. Also, we see interesting use cases for migration when users want to take a specific set of data and migrate it from one cluster to another. Even if it's a short-term, lived engagement, you can keep the cluster active. And this is one of the biggest difficulties in migrating data from one cluster to the other, is where do you draw the cutoff point? And with an active-active implementation, you can keep the clusters up and running all the time. Probably most importantly on the last bullet on the slide there is that name node and data node operations are fundamentally unchanged. We don't intercept any name node operation directly, so we're not modifying HDFS or any of the other file systems that we support, and we're not modifying the data node or any of the other file systems that actually the data lives on underneath it. This is all done as a client proxy, so it sits outside of the cluster essentially as a client. And as a client, then it functions like any other utility would inside of the cluster. Only in this case, it's providing active-active replication. So, the question is how many replicas do you really need? And this changes. In some cases, you need, a full data set for backup, where you may need data from data center 1 to your backup data center. A more interesting use case that we're seeing lately is in the results of a query, where what we want to replicate to multiple different locations is the answer to the question that you've asked of the query. And that answer may get distilled down again in each one of the different data centers and then replicated again. So what's interesting is when you create sort of a global or a true Hadoop data lake with an active-active implementation, you're able to utilize all of the nodes across all of the clusters. You can do lots of kind of interesting things like mixed heterogeneous architectures, high performance nodes against lower performance nodes that are more geared towards batch, and so on. And so the last couple slides I'll do here, and then I'll even do a quick demonstration to show you an active-active implementation, is talk about some of the use cases that selective data replication in an active-active format supports. The first one is what we canonically call the Saudi Arabia case, and that is that data can't leave the center of origin for reasons of foreign regulation, foreign sovereignty, and so forth. So that data has to be protected, both the data and the underlying metadata. So with selective data replication, we can ensure that that particular data set never leaves its country of origin, and in fact, from a Fusion perspective, it will not allow you to take that data and accidentally replicate it somewhere else. If you say it can only go between, sit in this data center or only in these two data centers in the same country, it won't, there's no mechanism to, without deleting it and re-adding it, to game it to another location. The temp case is, simply we don't replicate data that isn't important to replicate. So temp, trash, intermediary files that are created by jobs don't need to be replicated. This also supports the ingest-only case where you can create ingest-only clusters. So a lot of times we're seeing customers struggle around, I have, a single small cluster that we need to derive data from, or a single location that we need to derive data from. It's not even a cluster. And how do we get that to sort of our master clusters? Do we have to set up a Storm? Do we have to set up, Kafka, Flume, some kind of ingest mechanism? Well, with a replicated solution like this, what you can do is you can just set up an ingest-only data center where its primary role is to take in data and have it automatically pushed back to master clusters or other clusters where the data is useful. An example of what that implementation might look like, in this particular case, you can see the orange kind of dots are spread across the 3 regions in the world, for the far right in Asia, the South Africa and South America, the public folder, maybe a user folder that just goes to DC1 and DC2, and then a temp folder or a private or protected data that doesn't leave its country of origin. And these rules are very easy to set up and create. We also support, as I mentioned a moment ago, what we call heterogeneous storage zones. This is when data needs to be shared between 2 different clusters, but the 2 different clusters have drastically different hardware resources, so it doesn't make sense to put them all together as one. You might have some legacy nodes that have been sitting around for a long time that have, say, 48 gigabytes of main memory and are well suited towards doing batch-oriented applications, but at the same time, some of the newer data that you're bringing in, with 128 and 256 gigs of memory that you're using for in-memory analytics, and sort of creating these lambda architectures where you have a batch zone and a real-time zone and try to bring together a common query. But you can keep those clusters separate, and by having the active infrastructure underneath it, provide the most accurate and timely data to those underlying queries themselves. And then finally, and then I'll do a quick demo and take some questions. An oversimplification of the WAN configuration itself. In the out-of-the-box model for copying data between clusters, and that is, I'm referring to DISCP, you have an N-to-M communications issue where every data node needs to be able to talk to every other data node. And so what this requires is a very complex network setup for firewalls, for SOCKS proxies. And if you said we could bring it down to 2 connections per data node, it's n times n, so 500 times 500 connections if you had 500 data nodes in each location that security and sysadmins need to evaluate and manage. So for this reason, a lot of times this step is left out, but this leaves a very large attack surface. So by moving to a much smaller architecture where only the fusion nodes handle the replication between data centers, you don't have this end-to-end communication problem, and therefore, again, have that reduced attack surface. So I'm going to do a quick demonstration. We've got a good couple of minutes left. I'll do a quick demonstration of the product for you, and then I will open it up for a couple of questions. So what you'll see here is I have 2 data centers. One of my data centers is in Oregon. It happens to be a CDH 5.3 cluster. I also have a data center in Northern Virginia. These are in the United States. And this one's running HTTP 2.2. And I'm replicating this data seamlessly between the 2 data centers. Now, to control this, we use our Fusion dashboard. And the Fusion dashboard essentially tells us what the number of memberships are inside of the system and whether the system is running correctly. So everything is green right now. You can see the 2 locations on the globe where those actually exist. And again, green is telling us that there are no issues in the world as it pertains to replication status. We also see that there are 2 zones, the DC1 and DC2 zones, and no files are coming in and no bytes are coming in. But this gives us a sense of how much data is actually being replicated from each location. Now, the way we control replication, of course, is with the folders that we choose to replicate. Each folder gets its own state machine. And that means that we get better performance and throughput by having each folder be in its own state machine. And it also means we can also handle how the system functions under a network partition. So for example, in this case, you can see I have a folder called REPL1. It's targeted at zones DC1 and 2, so Northern Virginia and Oregon. And its current state is it's consistent. The data is strongly consistent or strictly consistent between the two systems. If I want to add another folder in there, I just simply click on Create. It presents a file system of the HDFS file tree. If I want, I can check the consistency right off the bat. And then I can choose REPL2 or any other folder that I want to replicate, choose which zones it replicates to, and then you got this other thing down here called the membership. Now, if you go back to when we talked a little bit earlier about the acceptor, proposer, and learner roles in the Paxos engine, memberships will let us define how those roles and memberships are created. In other words, how many acceptors do I have for a given state machine. And as I mentioned, each folder is its own deterministic state machine. So because I only have 2 nodes, I have a very simple setup here, 2 replication nodes. That's an even number. And I told you this is based on majority quorum. Well, one of my memberships has the majority quorum based in the Northern Virginia data center, and I'll create my second membership having majority quorum in the Oregon data center. Now, what does this actually do for me? It means that under a network partition, that my folder REPL1 will always be writable, even under a network partition by the North Virginia data center. And my REPL2 folder, even under a network partition, will always be writable by the Oregon data center. So let's go ahead and do this. I'll do a quick job. I'll run a job inside the system. And the way we'll do this is I'm just going to do a quick TerraGen job for about 20 files and 200 megabytes, something I can move across the network fairly quickly. And at the same time, so this window up here in the left-hand corner is running in Data Center 1. At the same time in Data Center 2, I'm going to just run some ingest, which is just basically running a group of files. It's a copy from local, doing a group of files. So it'll just kind of iterate through that file list. So I'm ingesting data in both these clusters, and right now the data is crossing. I'm writing into both clusters at the same time, and the data is crossing, the west and east coast, 3,000 miles between these data centers. These are real clusters. They're running in Amazon EC2 right now. And what I'm going to do is I'm going to basically break the network between the two. So I'm using IPsec as the tunnel between the two. We're not going to start it, though. We're going to stop it. And I'm going to stop the tunnel between the 2 data centers. Now, even though I have stopped the tunnel between the 2 data centers, I'll just show you that I can't SSH now into WD Fusion 2 from my 8 node. That's kind of locked up. There's no connection between the 2. You can see that both jobs are still running in each data center. And this is part of what it means to be running active-active. I can write into these folders. They're both trying to replicate, and as soon as the network is restored, which I'll go ahead and do now, then it will automatically take the GSNs, all those global sequence numbers, each one of those operations. In fact, it's easier to understand on the right-hand side. Each file that's coming in gets a global sequence number. And each GSN is being applied in the data center, in this case, the Oregon data center. It can't reach the North Virginia data center, but once I reestablish that connection, that same deterministic order of events occurs on the North Virginia side, and therefore it catches up and plays back all of the transactions that had been missed while the network was down. So now that the job is done, I'll just kind of quickly switch back to the client. Actually, let's look at it over here. And we can take a look at the data that's being ingested in Data Center 2. So let's go to our replicated folders, and we'll just look at our file transfers, and let's see which ones are complete. Yeah, this actually happened so quick I can't even show you the in progress. But what you can see is each file part that was created. You can see how big it was, what time it started at, when it completed, its elapsed time, and had there been some files in progress. Let me just hit recheck in case there's one more. Nah, they're all done. You'd also be able to see what the size is, what the transfer rate is, and how much time is remaining. And that's what it really means to be an active-active cluster, a single Hadoop cluster really across a group of zones geographically distributed across the world. So I'll open it up for some questions. Yes?
Working? Okay. Would it be a good idea to apply this active-active replication strategy for 2 clusters that is in the same data center?
Yeah. So, should we apply this to 2 clusters in the same data center? Yeah, I commonly see that this is a regular practice, because if you think about it, a lot of times an organization already starts with multiple clusters. And what happens is they start as siloed clusters, but over time, they start realizing that the data that they're creating or that the data that they're ingesting is useful to each other. But now they're in 2 different silos. So one is this will definitely allow you to do this in an active-active format where you can share the data. The other thing that we see oftentimes is with applications like HBase, where there's I/O contention for a MapReduce job running against H files versus the I/O contention of the actual puts in HBase. So by kind of separating these out, your H files, you can run MapReduce against the H files and not affect the region servers. And obviously a number of other use cases as well. So it's absolutely applicable to land scope data centers as well. Yes?
I have a question about how the replication works. So as far as I understand, first the metadata is replicated synchronously between the data centers, and then the data is replicated asynchronously.
Mm-hmm.
If we have a big data ingestion in one of the data centers, that will mean that the data won't be replicated. And let's say we have a job on the other data center that actually kicks off when it sees that the data is available, and it will be available because the namespace will be one, and metadata will be updated almost instantaneously. But the data won't be actually there yet.
You actually won't see the file. It'll kind of be in sort of a hidden, copying state. You won't see the file until it's actually complete. Until the file closes, the data won't be visible. What's important about coordination is making sure that someone else, if you start to ingest, that file foo, that someone else can come in and say, I want to do a make dir on foo, and then go put a bunch of stuff in it, and then we have to reconcile. They won't be able to do that. So we'll get the data there as fast as the network will allow. Typically what we see, if you've got like even a 2 gigabit pipe between data centers, you're talking, minutes to 2 minutes before all the data is available from the end of an ingest.
So basically we're saying even that the metadata is copied, it won't show that the file is on the other data center unless the data is already copied.
Yeah, you won't see it until the file is actually there.
Okay, thanks.
Or complete is a better way to say it, because it's technically been started. Any questions? Okay. Well, thank you very much.